Hi, my name is Daniele Di Sarli, and I am a PhD student in computer science. The work that I am going to present today is a benchmarking of reservoir and recurrent neural networks for human state and activity recognition. And my co-authors are Davide Bacciu, Claudio Gallicchio, Alessio Micheli, and Niccolò Puccinelli from the Department of Computer Science at University of Pisa, Italy. Well, say you want to detect the emotion of a human peer. We humans, we do that easily. We use the visual features, we look at the face, and we can recognize whether the other person is stressed, the emotion and the activity that it is performing. However, in general, this feature can be masked by the user, by the human, either intentionally or not. For example, a subject could have a physical impairment, so it is difficult to show meaningful, real emotions through the face. So this is a problem if you want to build a system that interacts seamlessly with a human. What it is better to do most of the times is to use signals such as EEG or ECG, which are more reliable and more difficult to be masked and produce better results. And when you want to deal with time series, if you want to build a predictive model, a natural choice is that of recurrent neural networks, which are naturally fit for this kind of tasks involving time series. However, we want models that are efficient in this context. Why? Because most of the times, systems that deal with the recognition of a human state are deployed on low-power devices, on low-power sensor. Maybe they run on batteries. So the training process must be really efficient in terms of computing power. And recurrent neural networks in general are not that efficient. However, there is a category of recurrent neural networks which is called acoustic networks from the paradigm of reservoir computing, which is notoriously really efficient for the training process. The question is, how do acoustic networks perform in this kind of tasks of human state recognition in terms of predictive accuracy? Now, this work is part of teaching, which stands for a computing toolkit for building efficient autonomous applications leveraging humanistic intelligence. And teaching is a project funded by the European Union, which deals with cyber-physical systems of systems. And in particular, with the observation that humans are a key part of these systems. In particular, if you want to build a human-machine interaction that is seamless, you must really make the machine aware of the human. So teaching deals with the aims to build a computing platform and a software toolkit for the development of applications which fall under this idea of human-centric AI. In particular, the results presented today are part of a demonstrative use case for the personalization of the driving style of a vehicle, keeping into consideration that there is a human there. Now, if you want more information about teaching, you can follow the link at the bottom of the slide or the social channels. So an important model that we have considered for teaching is that of acoustic networks. I review now quickly what acoustic networks are. So there are a recurrent neural network model, which is made by two components. The first component is a reservoir, which is a recurrent network. And then we have a linear readout. So the reservoir is the part of the network that is driven by an input signal. And the key characteristic here is that the reservoir is not trained. The weight matrices within the reservoir are fixed. You can observe at the bottom of the slide the equation of the state evolution of a reservoir H is the state at time t, and W and U are weight matrices. These weight matrices are initialized when the network is created and then are left fixed. They just need to meet some mathematical properties for the stability of this dynamical system. So if these matrices are not trained, the training is limited to the readout layer. The readout layer is described by this equation in its most simple form, and basically observes the state of the reservoir at a given time, and through some learned weights produces a prediction. So since the readout is the only component that needs to be trained, in the most simple case, this is the only matrix that needs to be trained. There is no need for backpropagation through time, because the time dependencies, the information about the time interactions, are naturally encoded in the reservoir. So the readout can exploit this information without needing training, which keeps into consideration time dependencies. And the result is a very efficient training approach. The question is, in addition to being efficient, do these networks also show some decent predictive accuracy for tasks of human state monitoring? We have decided to compare some models, some recurrent models on human state monitoring tasks. We have chosen 5 tasks from the literature: Wizard, HR, PAMAT2, Opportunity, and Aserpen. Now, some of these tasks are related to the recognition of emotions, others are related to the recognition of the activity of a human. For example, Wizard deals with stress, amusement states, or PAMAP2, for example, deals with the recognition of running, watching TV, driving. In any case, these are classification tasks. And the data in the datasets comes mainly from biophysical sensors, such as, for example, those found in some special wristbands. The models that we consider for these experiments are the following 4. So we have considered vanilla recurrent neural networks, acoustic networks, of course, long short-term memory, and gated recurrent units. The first one is a useful baseline. So vanilla recurrent neural networks are a useful baseline to compare to. And then long short-term memory and gated recurrent units are the most popular state-of-the-art. So we also compare against them. Note that all these models can be used in a multi-layer fashion. So we also consider multi-layer configurations to deep recurrent models. And I also want to point out that in the following results, we have, for a fair comparison, kept the number of free parameters equal for all the models, so that their performance can be fairly compared. Now, these are the accuracy results. You find on the horizontal axis the datasets and also the models. For example, you see in blue the vanilla recurrent neural network, then in orange the acoustic network, in gray the long short-term memory, and in yellow the gated recurrent units. Moreover, these results are the average of several repetitions with different random initialization. On the y-axis, instead, you find a measure of the predictive accuracy on the test set. Now, you can observe that in most of the cases, the accuracy is above 90%. And this indicates a general suitability, as expected, of recurrent neural network models for this kind of tasks. A second observation is that despite their simplicity, acoustic networks in orange, on average, are just 2.65% lower than the best performing model. This is, I remember, a model which uses recurrent parameters which are not trained. So it is an extremely simple model, but it is able to achieve very high predictive accuracy. And then gated models, as expected, often reach the highest accuracy since they are really complex models. If you remember, I have introduced you the fact that we allow the models to have a high number of layers. In particular, we can see here that the best performance comes with a number of layers which is greater than 1 in most of the cases. Again, on the axis, we have the dataset and the model. On the y-axis, we have the number of layers. So if we try to artificially restrict these models to just one recurrent layer, we can find out what is the contribution of this multi-layering. Remember, this was the average accuracy with multi-layer networks. We have repeated the model selection by constraining all models to one layer, and also, again, maintaining the same number of trainable parameters between all models. And we obtain this drop in performance. So as you can see, there is some large drop for recurrent neural network and a bit less in general for gated models. But in any case, we can see that, as expected, deep models are able to better represent the multiple time scales that are present in the data. In conclusion, for the kind of task under consideration, we have shown that acoustic networks are highly effective and can be used for this kind of task of human state monitoring. Now, you may wonder why acoustic networks and not long-short-term memory. Well, acoustic networks have unique advantages for practical applications. Again, the efficiency. These kind of applications are often deployed on devices which are wearable, which are low power, depend on a battery. So the training process must be really efficient, and acoustic networks are able to do that. In addition to an efficient training, acoustic networks also have a unique characteristic, which is useful in this kind of application, which is that of an optimal form of federation. So if you want to perform federated learning, which is really common in such cases of human state monitoring, acoustic network allow to obtain an exact aggregation of your weights, which is not possible with the other models. So in conclusion, acoustic network can thus serve as the first choice in common human-centric tasks. This is my contact information. In case you have any question, I'd be happy to answer with them. Thank you.